Hey there, welcome back to Calculus. In this short video, I want to show you how you can use the online graphing software Desmos to make a table of output values for a given function. You can then use those tables to investigate the values of limits of that function. We introduced the notion of limit in the lecture videos for sections 2.1 and 2.2. So if you haven't already done so, I would definitely recommend that you look at those. I'm going to be assuming you're familiar with them here. In particular, in the lecture video for section 2.2, we used, among other tools, the graph of a function, tables of values of outputs of those functions to estimate values of limits of those functions. So I want to show you in this short video how you can use Desmos to generate tables like I was using in that lecture video. Okay, it's a very useful skill. I'm going to just use the same example, one of the same examples that I used in the lecture video. I want to show you how you can use Desmos to make a table of values to estimate the value of the limit of this rational function. The limit as x approaches 3 of x squared minus 3x divided by x squared minus 9. Okay, so let me switch over quickly here. I've got a Desmos window ready to go. You can see it. If you're not already familiar with Desmos, I've got another short video to kind of orient you on how to use it. It's a very useful tool. I recommend you get used to using it and use it a lot. But I'm just going to come over here to where you input the values of the functions, and I'm going to put in the output expression for the function I'm interested in. I'm going to put in x squared minus 3x. And use a parenthesis, so I divide that entire expression by x squared minus 9. And Desmos has already generated the graph of the function, okay? And like we did in the section 2.2 video, we could use this graph to estimate the value of this limit. But I want to show you how you can use Desmos to make a table. So right above where I entered that function, there's a little gear icon. It's called the edit list. And if I click it, for each function that I've entered, here I've only entered the one rational function, I get three choices. I can mouse over them and show you what they mean. I can convert this function to a table. I can duplicate the function if I want to do something else with it. I can get rid of the function altogether if I'm done with it. Well, I'm going to convert this function to a table, clicking that icon. And Desmos, in a visually familiar way, shows me a table of input values x and the corresponding output values, the values that I'd get if I replaced x into that rational function. Okay, so it's done the arithmetic for me. It also has plotted the points on the graph. If I click on the coordinates of one of those points, it shows me the input-output pair. So when the input is -2, the output is also -2. That corresponds to the first row in the table. The input's -1, the output is -1/2. That's the second row in the table. And so on. The 5 points that are in the table have been drawn on the graph. They're their inputs with their corresponding outputs. Very powerful visualization. I'm interested in the limit as x approaches 3. I'm going to recenter this picture so that 3 is the x coordinate 3 is sort of closer to the middle. 3 is not one of the auto-generated points that Desmos put in. I could click on one of those and just replace it with whatever value I want, or you can make a new row. If I just try to enter 3, Desmos tells me that this function's not defined. 3 is not in the domain of this rational function. 3 makes x squared minus 9 equal to 0. Often, when we're looking at limits, we're going to be interested in the values of a function near an input value that's not really an input value. It's not in the domain of the function. Like, for example, here, x equals 3 is not an input for this function, but I can choose values near 3 and ask what are the corresponding outputs behaving like. Like, for example, I could choose a number like 2.5. 2.5 is within a half of 3. Desmos has automatically plotted the new point, and I can see that when the output or the input is 2.5, the output is 0.455 or more accuracy in the table. I can choose a number closer to 3. 2.9 is within a tenth. Desmos has plotted the new point. The output is 492. I can generate the new point. 2.99 is within a hundredth of 3. 2.999 is within a thousandth of 3. Okay, the points here are getting hard to distinguish because the inputs are so close to each other, but I can definitely look at the output column in this table and make an educated guess about what those values seem to be approaching. It's very important, and this was mentioned in the lecture video as well, but it's so important I'm going to mention it here as too, that it doesn't suffice to just look at values, in this case near 3, with numbers that are less than 3, 2.5, 2.9, and so on. All those numbers are less than 3. I also need to consider values that are bigger than 3. All right, so I have to look at the limit, quote unquote, from both sides. So 3.5 is a half more. I can look at 3.1, it's within a tenth. 3.01, okay? 3.001. I'm choosing numbers that are, none of them are equal to 3, but they're getting closer and closer to 3. Again, the picture gets very busy. If I kind of zoom in on that a little bit, I can see some more detail. If I click on any one of those points, it'll tell me which one I'm looking at. There's my input equal to 3.01. But looking at the output column of this table, I think it's reasonable to take an educated guess at what the value of this limit is. It seems the closer I choose the value x equal to 3, the closer the output is getting to 0.5. So I would conjecture that the limit as x approaches 3 of this rational function, x squared minus 3x over x squared minus 9, is equal to a half. Okay, I'm going to keep this video short. I hope that's useful to help you generate tables of values for functions that you're investigating in your homework and in your practice problems. So thanks for listening.